welcome to the Deep Dive. Today, you're joining us for a really fascinating look into our closest stellar neighbor, Proxima Centauri.
That's right.
You're here because you want the quick route to being, well-informed on truly interesting topics. And this deep dive absolutely delivers. We're tackling the big question of whether the planets around this nearby star, particularly one that's Earth-sized, could actually be habitable.
A huge question in astronomy right now.
And we're focusing on some brand new insights from the Atacama Large Millimeter Submillimeter Array, ALMA for short.
Exactly. For a long time, our view of Proxima Centauri has been mostly through what we can see with, regular telescopes' visible light.
Right.
But these new findings from ALMA, which looks at the universe in radio and millimeter wavelengths, are revealing a whole new side to this star, a much stormier side, perhaps.
Right. Now, the really exciting thing you might already know is that Proxima Centauri has at least one planet about the same size as Earth, orbiting within its habitable zone.
Yeah, the Goldilocks zone.
Exactly. That's the region around a star where the temperature could, in theory, allow liquid water to exist on a planet's surface.
Crucial for life as we know it.
But Proxima Centauri is also known to be a pretty active star, prone to these bursts of energy called flares.
Very active, especially for an M-dwarf.
So what we're really diving into today is how this stellar activity, especially these intense flares that ALMA is now showing us at radio and millimeter wavelengths, impacts the atmospheres of those planets and ultimately their potential for life.
Because it's one thing to be in the right place.
Yeah. Because while we knew about flares in visible light, the ALMA data suggests something much more intense is going on, maybe constantly.
It does. So let's get a bit of context first. Proxima Centauri is just over 4 light years away from us.
4 light years. Sounds far, but in space terms.
It's incredibly close. To give you a sense of scale, in the vastness of space, that's like being the next-door neighbor, cosmically speaking. It's what astronomers classify as a highly active M-dwarf star. Now, these stars are smaller and cooler than our sun, but as we're discovering, they can be surprisingly energetic.
Little dynamos.
Kind of. And the key point for our discussion today is that Proxima Centauri is known to host at least one rocky planet, roughly the size of Earth, orbiting within its habitable zone, that sweet spot where liquid water could exist.
Okay, so potentially habitable real estate right next door. Sounds great. But then we keep hearing about these flares. What exactly are they, and why should you, our listener, who's interested in whether life could be out there, be concerned about them when it comes to these planets?
Right. Well, think of stellar flares as similar to the solar flares that happen on our own sun. They're sudden, powerful releases of a huge amount of energy across the entire electromagnetic spectrum.
The whole spectrum, not just visible light.
No, the whole range. When we say electromagnetic spectrum, that's just, the whole range of light and energy, from the radio waves ALMA sees through visible light up to things like X-rays and gamma rays. Importantly, these flares also involve the ejection of very high energy particles, which we call stellar energetic particles, or SAPs.
Particles, too, like a blast wave.
Kind of, yeah. A wave of charged particles moving incredibly fast. Now, for a planet orbiting a star that frequently erupts with flares, these events can be a significant challenge, a real problem. These intense bursts of energy and particles have the potential to really mess with a planet's atmosphere.
Mess with it how?
Right.
What kind of damage are we talking about that would make a potentially life-friendly planet,
Yeah.
Unfriendly?
Well, imagine a planet constantly being bombarded by this intense radiation and these high-speed particles. One of the main concerns is atmospheric erosion.
Erosion, like wearing it away.
Exactly. It's essentially the stripping away of the gases that make up the planet's atmosphere, bit by bit, or maybe even in larger chunks during big flares.
And that's bad because...
Because within that atmosphere are crucial components for life as we know it. For example, ozone is vital because it shields the surface from harmful ultraviolet radiation from the star.
Like Earth's ozone layer.
Precisely. Water vapor is also essential for the possibility of liquid water on the surface. If these components are gradually eroded away by repeated flares, a planet that might have started out as potentially habitable could end up as a barren, dry world exposed to harsh radiation.
So, not exactly ideal conditions for life then.
Not ideal at all. It paints a pretty concerning picture for the prospects of life around Proxima Centauri, potentially.
So this is where these new ALMA observations come into play, giving us a better understanding of just how bad this flaring activity might be, right? Tell us about what makes these observations so significant.
Exactly. A recent study led by Kiana Burton and Meredith McGregor really focused on examining the millimeter wavelength flare activity of Proxima Centauri. They used both new data collected by ALMA and also looked back at archival data.
So combining old and new views.
Yes. And what's particularly fascinating for you, for our listeners, is that this is the most comprehensive look we've ever had at these flares across different wavelengths with a specific focus on that millimeter range.
Why millimeters specifically?
Because it allows us to understand aspects of the flares particularly related to those energetic particles that we simply couldn't see with telescopes that only observe visible light. It opens a new window.
And you mentioned Proxima Centauri is a highly active M-dwarf star. Why is it that these types of stars, and Proxima Centauri in particular, seem so prone to these powerful outbursts? It sounds a bit like a cosmic temper tantrum compared to our own relatively stable sun.
That's a great way to put it. The key difference likely lies in their internal structure. Our sun has different layers inside, including a radiative zone where energy travels outwards as radiation, and then an outer convective zone.
Convective, like boiling water.
Exactly like a pot of boiling water, yeah, where hot material rises and cooler material sinks. Now, Proxima Centauri being smaller and having a strong magnetic field is likely fully convective throughout its entire interior.
The whole star is boiling.
In a manner of speaking, yes. This means that hot material is constantly churning from the interior to the surface and back again throughout the entire star. This vigorous movement generates very strong and incredibly tangled magnetic fields.
Magnetism again?
Always. These magnetic fields can get twisted and stressed, like coiling up ropes, and when they eventually snap and reconnect, much like a rubber band breaking when stretched too far, they release enormous amounts of energy and particles. That's what we observe as these flares.
Okay, so it's like a giant stellar rubber band that keeps snapping.
Right.
And Meredith McGregor, one of the lead researchers, had a really insightful way of framing the main question they were trying to answer with this study, right?
She did. She pointed out that while our sun also has flares, and those can create beautiful auroras on Earth, the northern and southern lights.
Because we're protected.
Exactly. Because our planet has a robust atmosphere and a strong magnetic field to protect us. But Proxima Centauri's flares seem to be on a much more intense level, possibly orders of magnitude stronger or more frequent.
Sure.
And given that Proxima Centauri has rocky planets within its habitable zone, the crucial question for you to consider is, what are these powerful flares actually doing to those planets' atmospheres?
Are they survivable?
Or are they sterilizing? Are they just causing some chemical changes, maybe making weird atmospheric chemistry? Or are they so intense that they're completely eroding the atmosphere away due to the sheer force of the radiation and the stream of particles? That's the fundamental uncertainty they were hoping to shed light on with this detailed ALMA data.
Right. So after all those hours of ALMA observations, a significant 50 hours, you said, using both the main 12-meter array and the smaller 7-meter Atacama compact array, what did they actually find? What are the key things you should know about these millimeter flares that we didn't know before?
Well, the sheer number of flares they detected is quite striking. They recorded 463 distinct flare events just during their observations.
463 in 50 hours. That sounds like a lot.
It is a lot. These flares had a wide range of energies, from 10 to the power of 24 ergs all the way up to 10 to the power of 27 ergs. Now, to give you a sense of scale, even the lower end of that energy range is still a considerable amount of energy being released by the star in one go.
And are these long events or quick bursts?
Mostly quick bursts. The majority of them were relatively short-lived, lasting anywhere from just 3 to 16 seconds.
Wow.
It's like a constant, almost like a popcorn machine, a barrage of quick, energetic bursts. Pop, pop, pop.
Wow, that's a lot of activity packed into a short time frame. And you mentioned that observing at millimeter wavelengths gives astronomers insights into the particles associated with these flares. How does that work exactly?
Exactly. So while ALMA detects the electromagnetic radiation, the light, essentially at these specific radio and millimeter wavelengths, the way that light behaves, its characteristics during the flare.
Like its brightness or polarization?
Precisely. By carefully analyzing the characteristics of this millimeter wavelength flaring, astronomers can actually deduce properties of the high-energy particles that are being accelerated and blasted out by the star during these flare events.
So the light carries clues about the particles.
It's as if the light emitted during the flare carries a fingerprint, of the energetic particles that produced it. This is crucial for you to understand because these high-energy particles are the direct culprits in potentially stripping away a planet's atmosphere. They do the heavy lifting, so to speak.
That's a really clever way to investigate what's happening on the star and its potential impact on the planets, even from light years away.
Yeah.
Now, I recall reading something about how smaller flares tend to happen much more frequently than the really massive, powerful ones. Is that a general rule for stars?
Yes, generally.
And does it hold true for Proxima Centauri based on this ALMA data?
Yes, that's a common pattern observed in many stars, including our own sun. Astronomers use something called a flare frequency distribution to illustrate this. It's essentially a way of showing how many flares of different energy levels occur over a given period.
Like a histogram of flares.
Kind of, yeah. Typically, this follows what's known as a power law relationship, which basically means you see a large number of smaller, less energetic events and a progressively smaller number of very large, very energetic events.
Okay.
What's particularly noteworthy about Proxima Centauri, based on this LMA study, is that it's such an active star that they detected a significant number of flares across a wide range of energies just within their observation period. It wasn't like they only saw tiny ones and had to wait ages for a big one.
So they got a good sample size across the board.
They really did. It underscores just how flare-prone this star is, almost constantly popping off flares of various sizes.
So it's not just that there are a lot of flares, but there also seem to be a significant number of quite powerful ones happening relatively frequently, at least compared to our sun.
That's the picture that's coming into focus, yes, especially when you consider these millimeter observations. And there was another very interesting finding concerning the highest energy flares they observed.
Oh, yeah. What was that?
They noticed a distinct asymmetry in their light curves. Now, a light curve is basically just a graph that shows how the brightness of the flare changes over time.
Up and down.
Right. For these most energetic flares they saw, there was a very rapid increase in brightness. A short, intense burst lasting maybe seconds, but then the brightness took a much longer time to fade back down to normal levels.
So fast rise, slow fall.
Exactly. This extended decay phase suggests that some more complex physical processes might be at play during these most powerful events, maybe continued particle acceleration or heating. It's something scientists will definitely be investigating further, and it could have unique implications for the planets orbiting the star. Maybe that slow decay phase delivers energy differently.
Huh. Interesting. Okay, so we're looking at a star that's not only our nearest neighbor, but also incredibly active, constantly emitting these frequent and sometimes very powerful flares. And this new ALMA data is giving us a much more detailed view of this activity at these longer millimeter wavelengths. But maybe we circle back, why are these specific wavelengths so important? What information are we really gaining by looking in the millimeter range that we simply couldn't get by observing in, say, visible light?
That's a crucial point to understand, yeah. As Meredith McGregor herself explained it, the millimeter flaring appears to be happening much more often, significantly more often than what we typically see when we observe Proxima Centauri in optical wavelengths, the kind of light our eyes can see.
More frequent in millimeter than optical.
Yes. In fact, their analysis suggests that the frequency with which millimeter flares occur follows a different power law, a different statistical distribution than that of optical flares.
Meaning the ratio of small to big flares is different.
Potentially, yes, or just the overall rate is much higher. So the key insight for you here is that if we were only relying on traditional optical telescopes, we would be missing a significant portion of Proxima Centauri's stormy behavior.
We'd be undercounting the flares.
Exactly, and potentially underestimating just how much energy and how many particles are hitting those orbiting planets. It's like only seeing the tip of the iceberg when it comes to this star's activity.
So it's like we were only getting a partial picture of what was going on, a biased picture maybe, and these millimeter observations are filling in some really important blanks.
Precisely. ALMA's unique capabilities are absolutely key here. It's the only millimeter wavelength interferometer currently capable of making these kinds of sensitive and precise measurements.
Interferometer. That means multiple dishes working together, right?
That's right. An interferometer in this context isn't just one giant telescope dish. It's a system of many smaller antennas spread out, in ALMA's case, across kilometers. They work together electronically, combining their signals to act like a much, much larger telescope.
giving it super sharp vision and sensitivity.
Exactly. Especially sensitivity at these specific wavelengths. And these radio and millimeter observations allow astronomers to get a much better handle on the total amount of energy released by the flares and, critically, the energies of the high-energy particles associated with them.
Connecting back to the atmospheric stripping problem.
Absolutely. This information is vital for truly understanding the potential impact these flares could have on the atmospheres, the survival, the chemistry of any orbiting planets.
So, to bring it all together then, this deep dive into the latest ALMA findings reveals a Proxima Centauri that is even more active and potentially more challenging for orbiting planets than we previously realized.
Yeah.
Largely due to these frequent and intense millimeter wavelength flares that we were essentially blind to before.
That's a very accurate summary, yes. These observations have definitely added a significant new layer to our understanding of our nearest stellar neighbor. It's not quite the quiet neighbor we might have thought. We now have solid evidence that these high-energy events at millimeter wavelengths are happening frequently, suggesting that any planets orbiting Proxima Centauri are likely experiencing a much more significant and frequent dose of radiation and high-energy particles than we were fully aware of based on optical observations alone.
Which brings us right back to that fundamental question we started with. The potential habitability of those nearby planets, particularly the Earth-sized one in the habitable zone. I mean, this constant barrage from these newly revealed millimeter flares certainly complicates the picture, doesn't it?
It really does.
It really makes you think about just how robust a planetary atmosphere would need to be, or maybe even a magnetic field, to withstand that kind of assault over billions of years and still potentially support life.
It absolutely does, and it strongly underscores the fact that when we talk about habitability, it's not simply a matter of a planet being located at the right distance from its star to have the right temperature for liquid water. The simple Goldilocks idea.
There's more to it.
There's so much more. The activity of the star itself and the types and amounts of radiation and particles it emits play a profoundly important role in shaping a planet's environment and its ultimate potential to host life. It could be the deciding factor.
So as our ability to observe and understand stellar activity continues to improve, especially around these smaller, cooler M-dwarf stars that seem to be abundant in our galaxy and our, prime targets in the search for exoplanets.
Because they're easier to find Earth-sized planets around.
Right. It really makes you wonder what other surprises might be out there, perhaps even around stars we thought we knew well, like our closest neighbor. How might these kinds of discoveries, which reveal a more dynamic and potentially hazardous environment than we anticipated, ultimately reshape our approach to the search for life beyond Earth?
It's a crucial question for the field.
It's certainly a compelling thought, the idea of these incredibly active stars hosting worlds that might still find a way, somehow, to harbor life despite the odds. Maybe life adapts.
Yeah.
Or finds refuge.
Indeed. It highlights the incredible complexity of the universe and serves as a constant reminder that we are still in the very early stages of understanding all the diverse factors that contribute to a planet's potential for habitability. This detailed study on Proxima Centauri, made possible by the unique capabilities of ALMA, represents a really significant step forward in our ongoing quest to answer that fundamental question. Are we alone?
Absolutely. Well, thanks for joining us for this deep dive into Proxima Centauri and its surprisingly energetic millimeter flares. Until our next exploration, keep those cosmic questions coming.